All those in favor say aye. The ayes have it. We're talking healthy vision and the effects of spaceflight on human health. Hi, I'm NASA astronaut Tracy Dyson. Welcome to StationLife.
Houston on 2 for velocity confirmation. Step 4, 5, and 4, 6. We're moving on to step 5.
You want to go right now for that activity?
Copy. Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Hi, welcome back. This month on StationLife, we're going to look at how the unique environment of space affects the human body. In recent years, a new trend has been identified. It seems some astronauts from the International Space Station have reported vision degradation during their spaceflight. So research has identified a possible link between vision impairment and the increased intracranial pressure that's caused by the shifting of bodily fluids from the lower extremities to the upper parts of the body in microgravity environment. This is an area of intense interest on board the ISS, with implications for future exploration missions. So watch now, NASA scientist Jennifer Fogarty explain this phenomenon.
One of the things we've found over the years is that there are changes in astronauts' eyes. Initially, in the early programs, all the way through the first part of International Space Station, we thought those changes in people's vision, how they see things, was just temporary and minor. About halfway through our International Space Station experience, we noticed that some of the astronauts' vision changes were a little bit more severe in that they had a harder time seeing objects both near and far, and also the vision didn't go back to normal as quickly as we expected it to. So we started looking a lot more closely at the back of the eye. What we noticed was that tissue in the back of the eye became a little bit more swollen and the shape of the eye changed. But the big question is why? Why would someone's eye change shape? Why would the back of the eye become swollen? One of the major changes that we've been able to document and understand is how the blood volume shifts from your lower body to your upper body when you go into microgravity. So things happen like your nose gets stuffy, your eyes feel a little bit of pressure. It feels like you have a really bad head cold. Well, we think that that change in fluid volume and that shift might be behind those changes in the eye. We also think it could be affecting the brain and changing what's called intracranial pressure. Normally, we measure intracranial pressure through a procedure called lumbar puncture. In spaceflight, that'd be very complicated to do, and we wouldn't want to necessarily do that to our astronauts if we didn't have to. So we look at non-invasive ways of measuring pressure in your brain through your eyes or your ears, or how much blood flow is actually going to your brain using ultrasound. So NASA has a lot of work ahead to understand the use of these non-invasive devices, both terrestrially and in flight. Part of our job is to understand how we use these tools before, during, and after a space mission to compare the results. In the process, we determine kind of how valid these procedures are, how mature the technologies are, and how well we can apply them not only to spaceflight, but what would be appropriate for spin back to Earth.
So by now you've probably heard about the one-year mission that's going on right now on board the ISS. One of the focal points of this mission is to better understand how does the body react to prolonged spaceflight. It's imperative that we understand what these effects are and develop appropriate countermeasures, especially if we're going to go further into space on longer missions, such as going to Mars. So let's learn more about fluid shifts and ocular health on ISS.
Did you know the human body is made up of more than 60% water? And with that comes challenges we deal with in our everyday life. Hi, I'm Dr. John Charles from NASA's Human Research Program. During the one-year International Space Station mission, NASA will conduct visual impairment studies to learn more about fluid shifts and vision health. Here on Earth, some of us experience swelling in our legs, or get dizzy when we stand up too quickly, or suffer from elevated blood pressure. These common ailments faced on Earth are related to the amount of fluids in our bodies and how they are redistributed when we change posture. Remember swinging upside down on the monkey bars when you were a child? You may have felt a heavy sensation around your eyes. When astronauts are in space, they may experience a similar feeling as weightlessness causes fluids to shift to the upper body. With this fluid shift persisting for weeks and months in space and not just seconds on the monkey bars, pressure may build up around the brain and behind the eye and affect their vision. In the past, we thought this was a temporary problem, but now believe it may be a more significant concern. 2 visual impairment studies, which use non-invasive tools like ultrasound devices, high-resolution photography, and blood pressure monitors, will assess what happens in the body when fluid volume shifts before, during, and after long-duration spaceflight. Researchers hope to be able to predict the magnitude of these shifts and understand the causes of related diseases. Vision is a critical sense on Earth and in orbit, and it is imperative we learn more as we prepare for future missions to asteroids, Mars, and beyond. Patients on Earth suffering from similar problems may benefit from NASA's research of this syndrome and the increased focus on non-invasive measurement technique. To learn more about NASA's Human Research Program, visit www.nasa.gov.
When you're up there for 6 months, or in Scott Kelly's case, an entire year, it's really the working in space part that becomes kind of the thing you love the most. It's the thing that gets you through the days. You're working with these professionals on the ground, and a lot of them have spent their entire lives working on these science experiments, and here we are up there and we get to operate them, and it's really an honor to get to do that. And in many ways, those are some of my fondest memories of being in space. You get to work these experiments, and they're usually watching over your shoulder from the ground. And there was a lot of times where I would do something, whether it was fluids or with flame research, it really didn't matter. The investigator would just say, whoa, wait, do that again. That was incredible and totally unexpected. And that was what just made you smile big up there when hey, we've been flying in space a long time, but we are still doing research that has unexpected results every single day on the space station. And I really love that about being up there.
Hi there, we have a special guest for you. We have with us today someone who is no stranger to human health and spaceflight combined. Let me introduce fellow astronaut Dr. Mike Barrett.
How are you doing today? Tracy, it's really good to be here with you.
It's great to have you here with us. Thank you so much, Mike, for joining us on
My pleasure.
StationLife. So now the fluid shifts in the body in the microgravity environment. You are no stranger to this. You're familiar with it both professionally and personally. Can you tell us a little bit about it from both perspectives?
Well, like you, Tracy, I've had the opportunity to experience the fluid shifts. And so when we fly into space, a lot of things happen to us. And immediately when the engines cut off, we almost feel like we're hanging upside down. That's what I remember as being 3 years old and hanging from the monkey bars and feeling the fluid kind of rush to your head.
Yeah.
And you kind of feel full and everything there. And that's just one of the things that happens to you when you fly in space. But it's really an amazing thing because it's a small part of a very large change that happens to the human body. We start adapting to weightlessness. And so many different things happen, and at the end of this adaptation, we almost become extraterrestrials, if you will. Our body is different, it changes shape. The physiology changes, our blood flow changes, our heart changes shape. Everything changes. And it makes us better for spaceflight. It makes us function better in weightlessness. But it can leave some problems, especially when you want to come home.
Yeah, so kind of give a little bit of an example of what that problem will be.
Well, one of the big things that we've really recently discovered is a change in vision. And I was actually up there on my first flight about 5 years ago or so, and maybe 3 months into the flight, I noticed that I needed stronger glasses to read my checklists. And I thought, well, I know that some people have said they needed stronger magnification before, so let's see if we can find out something about this. Myself and my co-worker, Bob Thirsk, who was also up there, who is also a doctor, by the way. Doctors rock in space.
Doctors are great in space.
Thank you. But we looked in each other's eyes and we thought we saw a little bit of swelling of the optic nerve, which we thought, that's very unusual. And we talked to our really smart friends on the ground, and they actually sent us some special hardware that gave us really good looks at the back of the eye.
Oh.
And
First, I've got to ask, how were you looking at each other's optic nerve?
well, it's a good question. So on the space station in the medical kits, we have this little instrument that the doctor may hold up to your eye sometime and just take a real good look at the back of your eye. Yeah, that's a good one. So we can see things actually that we would be worried about as a doctor, but this time it gave us a chance to see things that are new as scientists. And so they gave us a much better camera. Within about 6 weeks, they launched this thing to us. And lo and behold, indeed, we did see some swelling of the optic nerve. We saw some other changes in the back of the eye, in the retina. And then we also did ultrasound that gave us a good look at the shape of the eye, and we saw some subtle changes. So we were starting to peel off the layers of something we had known about for a long time, but just didn't know why.
Well, you know, this is amazing. This is, not only is it great to have doctors that have this kind of expertise on board, but to have the curiosity propel them to look deeper, to initiate, I think, something that is very important not only to our health on board the space station, but to people on Earth as well. I think I want to not only commend you, but thank you on behalf of all of us, myself included.
I accept your thanks, but I also have to mention that there are so many really smart people on the ground who've been helping us do this. And some of them are doctors and some of them are researchers, and the problem is so big, the questions are so big that we just need lots of heads in this, and they're doing a great job. But what the human does when it gets into weightlessness, immediately the body shape changes. The chest actually gets a little bigger, the waist gets a little smaller. Sounds great, doesn't it?
Yeah.
And that happens pretty quick. And your internal organs actually move along with the diaphragm. It actually goes up a little bit more towards the head, and that's why your waist gets smaller. Yeah. All the fluid shifts to your chest because there's no gravity keeping it down in your legs. But really, all of that happens. Your heart changes, your blood changes, the way you regulate your body fluid changes. Your bone and muscles, unfortunately, start to come apart because they're not challenged by gravity every day. So we have to exercise really hard to keep those up there. But basically, except for that, you become adapted to weightlessness. You become an extraterrestrial.
You mentioned earlier about all the different investigators, all the different scientists and physicians who are trying to understand this phenomenon of fluid shifts in microgravity and the effects that it has on us. I know you flew on the space station before I did, and so going back to the no, that's not where I'm going with this. Right. The fact that so we can think about that time period when you first flew as when the eye problems started to be a subject. And then when I flew, which was I think a year or so after you did, we started to get instrumentation on board the space station to actually start investigating this. This is when the experts started to come together and say, "Hey, let's investigate this."
Right.
And now today we have a full complement of devices just to look at the eye, and that is not to say all of the other types of investigations that are going on focused on fluid shifts. And so can you share anything more that you know about those investigations? Because I know you work closely and collaboratively with all of those investigators that are involved in it. So
right.
Tell us a little more.
No, I mean
about
that's a great question, because one thing we can say for sure is that the issue with the eye is it's much bigger than the eye. It involves the brain, the optic nerve, a lot of the central nervous system, and it's not new. It's just that we missed it for many years. Now when we go back and look at medical records, we find that some of our Russian colleagues had similar things going on in the Mir station. And clearly, it's been happening since people have been flying in space. We know that also from looking back at our records. But we missed it because we didn't have the tools that we have now. We didn't have the flight experience that we have under our belts now. And so basically, we missed something very big, a global change that represents another aspect of adapting to zero gravity, which we didn't know. And why were we able to find it? Because we have this big, incredibly well-equipped laboratory. So in a way, the International Space Station is doing exactly what it was designed to do, providing a big laboratory with lots of flight experience and the means to discover really big things. Now, but I can tell you as a doctor that the first thing I think about is, boy, we need to understand this, because this affects everybody who flies, potentially. And it's not just NASA astronauts, it's whoever is going to fly in space afterwards. The second thing I think as a doctor is, what else are we missing? What else have we not found yet? And so it makes you want to be very aggressive in doing all the science, the investigations on the space station, because there are surely things that we don't know, and we don't even understand the eye thing totally.
I was thinking we need to send Mike back up into space.
Yes, we do.
Figure out what the next thing is we need to look at, quick.
But when you start talking about deep space missions, maybe a year in zero gravity or even 3 years out and back to Mars, we're going to have to ratchet things up a little bit. And there's several tools that we want to develop to be sure we know what best countermeasures to use for what mission. So certainly the heavy exercise we do is one of those. Artificial gravity is another thing we'd like to explore to know when to use it, what kind of missions might require it. So that would be a ship that spins, or getting into something that spins you for a little while each day to put back some of those G loads, some of that gravitational load from orbit. Certain medications that can actually protect, we're looking at those. It can actually protect the bone from coming apart, from softening too much. And our biggest problem is really radiation. And once you get out of low Earth orbit and out from under the magnetic fields that actually help to shield you, then radiation becomes much bigger problem for us. And so shielding material, being able to fly fast to wherever you want to go, and spending less time in deep space, that will probably be our biggest limiter to how much time we spend traveling, say, from Earth to Mars, right? So there's many different solutions. One of them is just to fly fast.
Yeah.
So.
Wow. So, and you mentioned like a whole arsenal of things that we can do to, that we call countermeasures, things which will help us to prevent the problems or counteract them. One of the interesting ones that is on board the space station right now is principally from our Russian colleagues, the Chibus.
Right.
So do you have any experience with that on orbit?
I've actually never been in the Chibus. I've trained to use it as an operator. So Chibus is actually a bird in Russian. It's the name of a bird that, and they name most of their suits, their space suits, after birds, which is really cool. But the Chibus is what's called a lower body negative pressure device. And what that does is it seals around your waist, and it keeps from your waist down to your toes in a vacuum chamber, if you will. Yeah, it sucks. And so literally it draws a vacuum down there, and all the fluids that shifted to your head, all of a sudden, now they want to go back down to your feet. So it mimics being on the ground again, which is really cool. Starting in a couple weeks here, we'll have a U.S. crew member doing LBNP for the first time in about 15 years, actually. It's really quite amazing. And so Scott Kelly, our one-year guy, and his counterpart, Mikhail Kornienko, will both be doing LBNP studies associated with the eye investigation.
Yeah, I flew with both those guys, by the way. Go
Yeah,
ahead.
and this will be pretty awesome for us because we'll be able to combine the Russian LBNP with ultrasound and other some of those special cameras that we use to look at the eye. And so we'll get a look at the effects of moving that fluid, really the fluid shifting on this eye phenomenon. And that's one of the big pieces to this puzzle that we've been waiting for a long time.
That is really exciting.
Yep.
And I'm telling you, the amount of work that we are able to get accomplished in just one 6-month increment, which is the typical stay for both Mike and I and a number of other colleagues we have. But to think about what we're going to gain in a whole year from both Misha and Scott is pretty exciting.
Yeah, we think so.
Looking forward to especially when they get back and find about how their experience was personally being up there for a year, because it's really just scratching the surface of what we hope to do in the future of going further into space.
Absolutely.
Yeah.
And I'm in contact with Scott pretty frequently, and I know two things are true. He's working real hard and he's having a great time.
That's two of the most important things.
Right, that's kind of what I remember.
Yeah, exactly.
Well.
Mike, thank you so much for
my
being
pleasure.
here on Station Life, and we hope to have you back again sometime.
Great.
Human beings want to go to Mars.
It's a fabulous destination for us to explore. It has so many scientific questions that we could answer, and it might actually be the first place where we find life beyond the atmosphere of our own Earth.
We're already working on what to do when we get there and how to protect the people who will make the trip.
We're doing quite a bit now, actually, in many different fields, medical, engineering, social sciences, to understand what we have to send people to Mars.
And much of that work is in progress right now on board the International Space Station. Since the first people flew in space, we've been studying how their bodies react in an environment where everything is up in the air, because they're weightless.
You may develop motion sickness. You will definitely have fluid shifts into your chest and head. You will lose muscle strength. You will lose bone strength. You will be receiving radiation that we don't receive on the ground, and we're not sure exactly what that will do. Exercise is a very effective countermeasure. That, coupled with drugs used for osteoporosis, have allowed us to eliminate bone loss in most or all of the astronauts that have done both the exercise and taken the drugs. But there's also the isolated, confined, extreme environment that the astronauts are in. And that's a challenge to the psychology and mental health and performance.
On the International Space Station, we've studied people in the space environment for 6 months at a time. But a Mars mission will take 5 times as long.
Mars missions may take 30 months start to finish. So I don't think it's a bad idea to start getting some longer experience on the International Space Station to give us an idea of what's awaiting us on these future very long flights.
So the station partners are taking the next step. For the first time ever on this vehicle, a pair of crew members is going to space for a year.
My first flight was very rewarding. There are certain times that are, fun. It is very challenging to live on the space station for 6 months. If we're going to go to Mars, we need to understand how the human body reacts in space for longer periods of time.
Человечество по орбите все время летать не будет. Нужно осваивать новые планеты, нужно осваивать Солнечную систему. Это неизбежно. И этот полет как бы первый шажочек вот на этом направлении.
Station science during this year will continue to study bone and muscle weakness and psychological effects. But there are new goals too, like gauging how being weightless for many, many months impacts fine motor skills and restful sleep, and evaluating readaptation to gravity.
After the astronauts land in Central Asia, after the one-year mission, we'll take them into a small tent and ask them to do certain very simple and very routine activities and measure how much they can and cannot do after the long period of spaceflight.
And the crew will use equipment that's already on board to try to quantify the fluid shift that is the prime suspect in vision changes, and maybe do something about it.
Wouldn't it be nice if we could change that fluid distribution in spaceflight and make measurements of the shape of the eye and other function and see if that really is the cause and the effect?
At the same time, Kelly and Kornienko and their crewmates will help with the development of technologies that will need to be improved if future deep space missions are to succeed.
The International Space Station is a test bed. It allows us to test our communications methods, perfect them, so that we know how to handle large delays later on.
Station robotics on ISS are developing tools that are going to assist crew members for future missions, especially long-duration missions to Mars. We're going to assist the crew members by having the robots do the repetitive tasks and also do the tasks that are in the dangerous environment that we don't want to subject our crew members to.
When we go to sit down and finally design the new next-generation regenerative life support for spacecraft to take us to Mars, we'll be able to draw on all the operational experience we've gotten with the space station systems to improve the system and make a more reliable and user-friendly system for the crew.
While fostering international cooperation and providing benefits to people on Earth right now, and serving as a destination for commercial vehicles and research, the International Space Station is enabling future space exploration. The trip to Mars starts right here.
Okay, so on this episode of Station Life, we learned about vision changes in space brought on by the fluid shifts in our body due to the lack of gravity on board the International Space Station. We also learned how we're studying this phenomenon and what we're doing about it. This vision research provides insight into the structural changes that can occur in both the eyes and the central nervous system, which can be relevant for patients here on Earth suffering from a wide range of ocular diseases, such as glaucoma. As you can see, research on board the ISS continues to benefit us all here on Earth. So be sure to stay in touch and follow us on Facebook and Twitter for the latest research news. And do not forget to download our new app on your mobile device. Until next time, we're working off the Earth for the Earth.